compiled, and the queries are often generated by computer, is written by human. But one thing I'm very sure here is like query play a very important role in the modern industry, and people no longer able to afford 5 years to find a bug. Otherwise, it's probably a lot of money already lost at that time. So like the way people are trying to solve the problem now, like instead of asking like human to just think about why it's going to run, you're trying to ask computer to solve it for us. So basically, you just have a tool. It's called a computer or tool or solver or anything. You just want to provide two queries you want to check against, and some property you want to check against. So the tool will try to either find the example that's showing that the query here are different, or just tell you they always return the same result, so they are equivalent. But of course, this problem is like undecidable. It's as hard as a halting problem, so the computer will never able to figure it out. So what people do now is basically to, like, beside the query and the property, also provide a bounded search space to allow the tool to traverse. It's basically the goal now here is to, okay, I give you the search space. Now the computers are trying to help you find a table in the search space such that the output, the two queries are different, or just prove that there is no possible table in the search space that will show their difference. So you get a bounded guarantee of the equivalence. So this process seems really nice. You just don't need to do anything, right? Just put the computer and the solver will just do the task for you. But actually, I mean, just before that, let's just show a concrete example here. So there are two very simple queries with select from where, and they have different predicates. They're pretty different. And you just show the search space like all tables within about k rows, and the property is that whether they're equivalent, and the solver will try to figure out the result for you. This is very nice. But like the problem here is that there's a lot of ways the solver can just get panicked when you provide something that's hard for the solver to solve. I mean, it's not a mystery, but it's just always the case. So for example, a query is not always select from where, otherwise we don't care. It's often contains like grouping and aggregation. It's all kind of equivalence of for loop and recurring in our program typically. And the search space seems okay. They only have k rows. They actually represent an exponential number of ways to partition the table. Like you have a table with k rows, it can be a case all k tuples belong to the same group, or everyone belongs to a different group, or anything in between. It's exponential. And also the property seems okay, but it's also very hard to check. If you ask a test engine, you will spend a lot of time trying to check the property, or if you throw it to SMG solver, the solver just need to digest the enormous constraint generated. So the real thing in the practice is that they always come together. The queries people care about are complex queries, and the search space they care about is big search space, and the property they care about is the complex property. It's just like this kind of seemingly nice problem is really hard to solve in practice. So the way to solve the problem, in our view, is to just break the chain. All three things come together to make it very hard to solve. Let's just break one thing. And I just decided to deal with the search space. So our idea is basically motivated from the small models thing in the model theory. It's basically, now I'm just asking a computer to search for the search space with all tables with the most k rows. I'm trying to find a smaller search space that is easier for the computer to traverse, but also give you the same guarantee. So that's kind of a small model thing. Basically, you have a smaller, cheaper way to check the property, and that can give you a guarantee of the problem. So let me just show this in detail. By small model, it's really meant to be sound and complete in terms of the property. So basically, it means in the smaller search space, if you can find a counterexample in the bigger search space, you must be able to find some counterexample in the smaller search space. In other words, if you cannot find any counterexample in the smaller search space, you're done. You don't need to go to the bigger space anymore. And so this just gives a guarantee that it's complete for reasoning this task. But of course, this is not going to be free. Otherwise, the world is so nice. So our way is to basically do an analysis conditioned on the queries we generated and the property. It's basically just for the task you provided to me, I'm going to do an analysis to figure out what is the smaller search space you can carve out to complete reasoning without losing any information. So this is what we do. This is an insight from the property. So actually, a lot of the very important property, they're very hard to check, whatever, but they have satisfied this kind of property. It's basically if you want to prove that two queries are different, you don't need to show their output are totally different on every row, different on anything. You just need to show there exists one row in their output. It's able to show a difference, right? So for example, this is a table that makes a Q1 and Q2 to produce different results. As long as you find in the output of Q1 and Q2 have one row that's different, like there's R in the output Q1, but not in the output Q2, And it's done. You don't care about all the gray area. They may be equal, they may not be equal. You just don't care. You are already able to find counterexample. So this will give us some intuition here, because you only care about one row in the output. Why don't you care about all parts of the tuples in the input, right? So the idea here is that we just need to figure out what are the things in the input that is responsible for generating this output. And the idea is basically if we figure out what are the things responsible for generating R, we can just pull it out. And it's also a counterexample to show the difference. So this means we construct a smaller table that's also able to show the difference from the original one. So the way to perform this analysis is called like provenance analysis. It's basically tracking something in the output, like what's the input responsible for that. So in practice, we will try to solve the problem. No one is going to tell you the R except yourself. So we don't know. We just assume there is a symbolic output. It's the output within the form of AB here. And just assume there is an input table that's going to show the difference between the two queries. So here, the queries are different because one is max, one is min. It's kind of obvious they're different. And now we just analyze what part of the input table is responsible for generating that. So we no longer need to consider all the other gray area to save our save a day for our solver. So it's very interesting here. So because you know the output is AB, although I never told you what is A, what is B. But one thing you're absolutely sure is that it only comes from the group in the input table that also has ID A, right? If the input, the other tuple have ID is C, it's going to somewhere in the gray area, have nothing to do with the thing we care about. So it basically means like here we just define the table, which is a carve out from original table, is the table have exactly the ID A. It's really nice because we don't really assume what's the AB. It's just representing a spectrum of tables. So in this way, we actually already covered out the search space from the original one. It's basically the search space containing all the tables is actually one group. The group with ID A, because A is symbolic, so it represents a space. So let's just see like what actually we save in our carving here. It's basically there are two tables show the difference. The one only is able to show a difference here on the, so basically one has like, the first one contains two groups, the second one only contains one group. And actually, in our smaller search space, because we only consider table with only one group, and the second table is included, but the first one just is thrown out. So we just save some energy. We don't need to search for two to show the difference, but we just only search for one. So meaning that smaller search space is enough to deal with the problem. So we just do some very nice work on just formalizing the algorithm and just trying to basically, I think the key idea is just this, but we just want to generalize for different operators, for different queries, because the query can be composed from all possible operators in a different way. So we inductively define the analysis rule of different operators, like how to do the backward analysis from the output to input, and also how to combine together when there are multiple queries. Like in equivalence, actually two queries doing something together. And the guarantee is like what I said. If you cannot find anything in a smaller search space, you're done. You don't need to visit a bigger search space. And also this analysis is a linear analysis. We just need to go one pass from the output to the input to figure out what are the responsible for generating the output tuple. So we need to do some experiment to show actually it's useful. So we just evaluate on two tasks. One is boundary verification. We are using 46 rules from Apache calcite. It's kind of like industry standard optimizer. It's kind of adopted by a lot of companies already. And another is a test generation. I just want to show whether a query can generate empty output or want to just show the student solution is wrong. And we're using student submissions and some examples from prior work. And the way we evaluate that is basically we just measuring the time with and without space refinement, like how much time the solver will consume in a bigger search space versus a smaller one. And basically run the thing twice and to compare the speed up. Also, one thing very interesting here, like in talk, I always talk about solver, but I never talk about what is the solver here. So it sort of kind of means just like solver is kind of generalized to different solvers for the problem. So we're evaluating on two different solvers. One is coset, one is Quex. They are both SMT because in the verification task we need to do a complete within a search space. But they have different encodings, and we're just trying to show the approach is actually only dealing with the search space, but not the specific solver implementation. So the first experiment is for verification. So here is a chart. I'm just trying to see the standard yellow one is just normal to 1. And the red part is like how much speed up we gain after the space refinement. And those are the results from different solvers. So one thing is just like we just figured out is that there can be a significant speed up in some cases. And also the speed up is pretty generalized to different solvers. And also, like, there are some like tiny slowdown in some cases, just because the analysis time is linear, so it's really small. And also, let's show some example like what really gets speed up a lot. And exactly the cases contain like grouping and aggregation, where we're breaking the groups from exponential to just constant number that give a lot of save. And in some cases, we are not able to speed up. It's like there's some queries called like Boolean queries. Like you can say the output is only at tuple 1, but then the whole body is going to decide how many times the 1 is going to appear. So basically, it's a very practical one. It's just like checking something basically. And so like in this case, our analysis decides everything in the table is guilty for the output. So we just cannot be able to carve out a smaller search space to do the reasoning. And so in this case, we just don't get any speed up at all. And also in the case of test generation, it's pretty much similar. We're able to show speed up on some cases, like when they are about to require multiple group, and with the speed up is a little bit limited in the case that the counter example actually is very small because it's kind of marginal to gain. So there is one limitation, obviously. I'm not sure if obvious, but yeah. So one thing, like I'm just assuming for properties that require one output tuple to show the difference, right? So it's able to check some very important properties like equivalence checking or like empty stuff. But actually some other property cannot be solved immediately. But I think one thing to extend that is basically to analyze the property and the query at the same time in the analysis process instead of just analyzing the query and assume the property is static. And also our analysis is just like one pass backward analysis. So you lose some precision in figuring out what are the things important for the output. But you can increase the precision using a more precise analysis. So this kind of summary, we do symbolic reasoning to make sure queries are doing good stuff. And we want to scale it up. And the way we scale it up is basically to cover a smaller search space to achieve the same guarantee as you do in the bigger search space. And our experiment showed that we have a lot of speed up on some cases, quite a lot. And also, I want to show like one takeaway message from my work. It's basically a solver is very likely to get stuck whatever problem you try. And like from my personal view, it's basically you could do some high-level analysis. It may be cheap. It's able to help your solver a lot. It may just save you another day. OK, thanks.
Thank you very much. Questions?
Hi, nice talk. Thanks for that. So you said to refine the search space, you do one pass through the full table, and it's a linear pass, and then you just refine it.
Yep.
I'm just trying to understand what the intuition is. Like, it kind of feels like you have to look through what you've already selected. So it's kind of like quadratic, I would think.
So actually, like, provenance analysis is something in database already. It's basically just you want to analyze what the things are responsible for something in the output, basically. So I have actually a backup slides here. It's hidden. So it's basically like what are responsible for the output is actually requires some precision. There are cases, actually the most responsible thing is only one tuple, but you can be a little bit more relaxed in some sense. Like everything is responsible or part of the table is responsible. So this analysis really, or doing a one pass way is a cheaper way to do it, something in the spectrum between. And it's kind of trying to do the trade-off between the analysis precision for pruning and the analysis overhead, basically. Yeah.
Let me ask you about scale of how the algorithm scales with the size of the input.
Yep. Oh yeah. So actually, we are able to speed up more when the input is bigger, because especially for aggregations. But I would say, like, just trying to push forward, there's still some guarantee because input space also grows exponentially in the case. It's actually quite a lot of dependency on the query structure. The hardest part is not the query size, it's not the input space, but actually what the operators query contain and how they operate. It's like the Boolean query is very hard to solve, for example.
Other questions? Very good. Thank you very much again.
Cool. Thank you, everyone.